My name is Jim Hazard. I work for ITASCA in the Minneapolis office. I have the honor to introduce our final keynote speaker, Dr. Mark Diederichs. Any of you who are working in rock will almost certainly know Mark already. However, I will read through the bio here, just so you can fill in the details. He's, like myself, born and bred here in Toronto. Did a bachelor's and a master's at University of Toronto. The master's that you did eventually led to the creation of DIPS program that many of you are familiar with. I think that's true. After Toronto, he went to Sudbury and worked in the Rock Mechanics Research Center at Laurentian. While he was there, he also completed a PhD. And we were talking last night, as part of that PhD, he was actually using PFC version 1. So one of the pioneers of using PFC. Finished the PhD in 2000 and then became a professor at Queen's and has been there ever since. Very, very long list of papers and research topics. Certainly not going to read them all. Almost certainly if you're in rock, you will be familiar with the Hooke and Diederichs equation for calculating Young's modulus in rock masses. The research spans all kinds of things related to rock mechanics and rock engineering. I'm certainly interested to hear what he's going to say about that. I will say when I was looking at the bio, one of the things that really stood out was the amount of students he has supervised and the amount of students that you almost certainly know that he has supervised. He's had a very large influence on educating people in the world of rock mechanics. I counted 29 PhDs supervised and 48 master's theses, so this is certainly an impressive contribution. But I'm looking forward to hearing about some science. So take it away, Mark.
Thanks, Jim. Before I started, there's 3 people in this room actually who got me started in this world of both brittle simulation, but more importantly, PFC. He doesn't know it, but Richard Bathurst in the front, I read his thesis and it changed my life back in the day. I thought, this is so cool. What's this and then I realized there's a whole other camp doing particle modeling as well, which of course I see Dave Patyandi. We exchanged a lot of emails in the early 90s or mid 90s, I guess. And of course, Peter Kundal. So with that, I'll just, I'll launch right in. So this is a little bit of my journey, I guess. 35 years of, I'll call it practical brittle fracture simulation. There's been lots and lots of modeling and analysis over the years that wasn't really available to the common person. But I'm going to throw out the question now. Peter Kundal had a question yesterday from with these models getting fancier and fancier and going into black box territory, are we losing touch with mechanics? And that's a sort of an underlying theme here as well. The models are nice, but do we really know more than we started years ago? So I'm going to talk specifically about brittle damage, also known as spalling, although that's just a manifestation. Starts off with boundary parallel fractures, either at the grain scale and can gradually get larger and larger, can interact with other structures. You can see in the middle top picture, that's grain scale extension damage under compression, all the way to on the bottom right. That's not too far from here, Niagara Tunnel. That's almost 4 meters of brittle spalling interacting with latent bedding planes. Very common problem in all sorts of rock mechanics, both at depth and I'm learning now not so deep. But it fundamentally starts with some sort of a way of generating an extension crack in compression. And the classical model for this, way back to Griffith, was the shear flaw, which could move in compression, generating singularities and creating a crack. And we make that big leap from that model to what we see as visible macroscopic excavation scale spalling. And how do we get there? You first get, obviously, you have to start at the grain scale. So you can see some scaled pictures here of extension fractures starting from some sort of a shear flaw on the left. It's fairly obvious. In the middle, it starts to cross grains and become the actual fractures become longer than the flaws that created them. And then eventually what we sort of skip a step because we don't see it happen, but we can see this excavation scale fracturing. So how the challenge back in the early 90s was how do we sort this out? There was a lot of evidence that it was happening, a lot of lab testing, particularly at the URL in Manitoba and other places, South Africa. But what's the process here? Fast forward, we have all sorts of ways of creating what we might call brittle damage models, either with continuum models, simply playing around with the plasticity parameters to fake brittle fracture. We can go to something more like UDEC, a discrete element model, to create brittle damage propagating through. You can see that the key here is that the yellow in that model, middle figure, is actually extension or tension. And only when you get farther out into the confined rock mass do you induce shear. And then we have complex models to look at interactions between structures, bedding, and brittle fractures in all sorts of different rock types. And these all look great, and they all seem to simulate something. But if you've ever seen Wizard of Oz, you know that the first part and the end and the last part of the movie are in black and white, because things are simple in Kansas. We have time to think and figure out what's actually happening, right? And that's what we used to do. We used to think about the physics of the problem. But now we're into this wonderful, how do we get rid of that? Well, that's going to be a problem. How do we get rid of that thing on the bottom? Oh, well, okay. So now we're into this world of colorful modeling, and the big question is it real? So if we go right back to the beginning, Griffith was actually an aircraft engineer trying to figure out why windshields cracked on aircraft, and he came up with the idea of the inherent flaw, both in tension. It was extended into compression. And the idea is that this flaw in tension starts to pull apart. You get singularities at the ends, and they propagate. The longer the crack, the bigger the singularity, the more the crack. So this tension crack would extend. If you think about in compression, you have to drive some sort of shear mechanism to create those singularities, but the physics is very similar. So in tension, that's going to be very annoying. I don't know if there's any. Oh, there we go. Okay, got it. So in tension, I often used to say first crack wins. So it's actually quite easy to figure out when damage begins and ends in a tensile situation, because of this idea that the longer the crack, the less stable it is. It's an unstable crack. As soon as you induce the first crack, the system will break. Now, following on from that, this model, this shear model, was also good in compression to predict when things start. But if you do the math on any of these models, you find that the cracks stop very quickly as soon as they enter into because the world is in compression, sigma 3. You have extension deformation, but the world is still under confinement. And as soon as these cracks go off on their own into the world, they stop pretty quickly. So that's a problem. What's wrong with this model? Things got even harder when attached friction to these cracks. The original Griffith crack was open. But of course, cracks are closed. So if you introduce friction, things get even harder to break and propagate. And it quickly becomes apparent that the only way you can propagate fractures through a confined medium is if these cracks interact. So this whole simple idea of fracture mechanics starts to get very complicated. The first crack is only the beginning in this case. But there was some hints of progress. Grace, Paulding, and Schultz published some great data back in '66, which I think is the last time the least one, which showed that the onset of lateral dilation in moderately reasonably slow loading happened at about half of the UCS, a little less than half the UCS. That's very familiar to most of us now. It had a slope in confining stress, axial stress space, sigma 3, sigma 1, whatever you like, which was non-zero. But it's hard to imagine that this was actually frictional. Perhaps it is, but you can see that looks very much like if we do lab tests today of any kind, we get the same relationship for the first onset of dilation. But as we know in the test, it keeps going up to peak. Those cracks can't really fully damage the sample. We can record them through AE, and we can record them through strain measurements. Everett Hook and others, I'm sure, did some experiments to show that in fact this idea of crack propagation, which is key to these cracks going anywhere once they start, is extremely sensitive to confining stress. So sensitive, in fact, most models don't really have enough detail and gradients in this regime to help us. But you get the idea. As sigma 3 over sigma 1 drops, or sigma 1 over sigma 3 increases, down to, in this case, sigma 1 over sigma 3 around the 10 to 20 mark, only then do you get cracks propagating any distance beyond their initial dimensions. And that's really critical to how fractures work. This is not the same confinement dependency that was developed by Mogi through lots and lots of triaxial testing. Mogi's line is actually also important. It was an empirical line based on how tests behaved, but if you run it through with reasonable values of Poisson's ratio, you realize that this line marks the extension fractures can occur on the left side of that line and above it. There's no extension strain on the right side, just from elastic theory. And if you have no extension strain at all, everything's moving inwards, you can't create extension cracks, period, even small ones. And so this is the dividing line between truly ductile or strain hardening or shearing behavior and brittle behavior. So you have these two thresholds, and you can see them here. The Mogi's line, if you will, with sigma 1 over sigma 3 less than 5. And this hook line, when you start to drop below 10 to 20, in one case, above that 5 line, you have purely shear behavior. This is the stuff that soil mechanics is based on. And we, without these three gentlemen I just mentioned, by the way, we'd be still pretending that rock is soil and just making the numbers bigger. But that's the soil behavior. In between, you have extension fracks coalescing to form shear cracks, and then below that, you actually have this brittle fracturing. And that lets us divide the world nicely up into true tension, spalling, tension cracks leading to, we'll call them shear zones, and then pure shear past Mogi. So this is the beginning of understanding the world of fracture. And thanks to a lot of good work in the past, Dr. Fairfish doesn't seem to be here this morning. Had some nice drinks with him the other night. We talked about this. You can see here in these wonderful graphics from this paper that the fractures begin on the external edges of this, in this case, the cylinder. The center is actually functioning in that shear mode throughout, and then eventually it just gets too much and you have final fracture. So this is one of the more significant figures in rock mechanics, in my opinion, this process that now we take for granted. This is a great paper that showed that this idea of shear cracking leading to tensile extension didn't need a shear crack. Anything that causes any modulus contrast, any sort of compliance issue, indentation within the sample, anything that can create disturbance in the force, as it were, can lead to extension cracks. So heterogeneity is key. In the same paper, they identified, I don't know if this is the first time, it's the first time I found, they identified this onset of dilatancy in a test, confined or unconfined. At some point, the linear behavior, the linear axial stress strain behavior starts to go nonlinear. And then, of course, you have failure in post peak, and they describe these as in this way. So you have initiation from multiple sources, short isolated cracks. Those cracks cross grain boundaries, start to interact, and then finally you have it becomes so much that you have a macroscopic shear process. And so this, a long time ago, with physical reasoning, was the basis. And what's going on here? Okay. I'm frozen. Yep. I am frozen.
Wait.
Maybe just.
Oh, what the heck?
Hang on. Let me just try this one. Oh, it's because I'm. Nope, no idea. Hello. Okay, here we go. Next. Nope.
Didn't work?
Nope.
Wait.
Can I just get out? Is that?
There we go. Use arrows.
Okay. Thanks. Is that going to work? Yeah. So this coming back to this idea of these thresholds, which are now sort of ubiquitous, and we test for them and have lots of discussion about them. It's basically the first point where you start to get extension cracks within a compressive field. Those then extend. Once they extend beyond the grain boundaries in a crystalline rock, at least, for example, they start to control their own destiny and they start to interact with other cracks. And that's when things really get interesting. And in some cases, that's when your sample fails. That's usually the best you can do in situ in any sort of term beyond a few minutes. After that, anything that happens after CD is really a function of the testing or the constraints. And we can test for these things. I won't get into details here, but with all sorts of acoustic and strain sensors and extensometers and whatever, we can look for deviations in the lateral and axial strains to try to identify these thresholds, which are part of the strength model. Acoustic emissions have been very successful. So these are just ways we can get inputs into models. And we have some empirical basis for all of this. This is a work that just appears everywhere. These are a bunch of case studies that were done in the 90s out of the GRC in Laurentian, but the case studies are international. But these are cases where people went into where rock had failed and excavated everything they could excavate back to the truly intact rock. So this is kind of a maximum damage, and you can see that it begins at about 40% of the UCS, but more importantly, it begins at CI for most rock masses. So this is empirical evidence, and you can track the damage. So this is just evidence going to the point of, okay, something interesting is happening here doesn't follow the normal rules of plastic modeling and so on. So modeling history that helped this all happen, of course. This is not the first program to analyze stresses. It's probably the first one that people could use. It's elegant boundary element stress model contained. I think it's about 4 pages in the back of Hook and Brown, 1980. Of course, he used pen plots. That computer there is actually what I started working on in my research. And of course, around the sort of in the mid to late 80s, ITASCA started releasing commercial packages. I don't know if I think I've got these dates right. I remember the floppy disk of MUDEC showing up in the lab, which then became UDEC later. UDEC was around as a mainframe program. FLAC and 3DEC came a little bit later. This was the beginning of usable models for geomechanics and rock mechanics and even soil mechanics, really. Coupled with work at U of T, which was happening around the same time, bringing boundary elements and finite elements to a point where normal people could use them. And this was a big boon for graduate students, because you no longer have to, as a grad student, you don't have to develop the program. You could just launch right into your research. This is another program, 3D boundary elements, that was around in the I'll say early 90s, and I used it with data from Landry and Oliver to analyze this important case history when Creighton was changing. They couldn't mine with cut and cover or mining anymore, or cut and fill mining anymore. They had to change. The stresses were too high. So this was the first time they did sort of VRM block stoping, and they were analyzing the stresses and taking very careful measurements through boreholes and observations of damage as they progressed this sequence. And when you analyze that, the black dots, the black squares are yielded rock masses, and the white are apparently intact rock. And what's kind of neat is if you overlay GSI models or intact models, even Griffith, it doesn't seem to work. But if you want to separate this data, you end up with a couple of choices. We originally started saying that sigma 1 minus sigma 3 equals a constant, half UCS. That's not quite right and causes problems. The reality is it's about 50% of UCS plus a slope of about I use 1.5 of sigma 3. And this seemed to be pretty neat. And what it allowed us to do in elastic modeling was a whole bunch of really exploit that 3D world to try to understand where we could expect this sort of brittle damage from the URL to Brunswick mine to this is a tunnel in Europe. And we got pretty good at it. It wasn't telling us anything about mechanics, but it was telling us what we should expect and where we should expect this kind of behavior. This is the Gotthard TBM. That's Dr. Marlon Villeneuve. She's a professor at Leuven now in Austria. But again, simple model, Simple, simple. So what do we know? Well, wall strength seems to be around 40 to 50% UCS. That corresponds to what we see in the lab as the onset of dilation. We know failure modes initiate through extension fractures. It seems to be a low friction process, and I say friction in the general sense of confinement dependent strength. It may or may not, we don't know if it's friction or something else. I have a lot of ideas, but that would take another talk. We know that rock under low confinement fails by spalling. If you increase the confinement, you eventually get to shear bands. Great. How do we model this inelastically with some sort of idea of what's really happening? So at this point in 90s, this was sort of empirical. And how do we tackle this? And so you start to think about this idea of trying to create extension in compression, and you eventually get to this point. All my friends are having kids at this point. You have those annoying child gates that you have to that sort of expand into the stairwell. And I was always thinking about that. And then of course along comes PFC, and I'm like, aha. And you can just see graphically what I'm talking about. This idea of inducing extension even in a compressive field. So extension strain within a compressive field is what is really how PFC models brittle fracture. So I took that in the early days, and this is fairly simple. You'll see a lot of versions of this, but it was kind of eye-opening at the time, was that you could create totally realistic fractures, or totally realistic yielded samples, which appear to be shearing at the end of the day, almost entirely from tension cracks. So these are axial, more or less pseudo-axial tension cracks within PFC, particles pulling apart, very few shear cracks except right at peak. But this idea that most fractures could be entirely induced by the onset of these microfractures. Even in compression, although as you start to increase the compression, shear starts to become more important. So this is damage evolution within a sample, starting to look great. Makes a lot of sense. But what is yield in a rock? For the longest time, rock mechanics was the only discipline that didn't talk about yield. We always talked about UCS, which is essentially ultimate strength. No engineer designs for ultimate strength, but we never talked about yield. So yield in a brittle rock, and this was kind of this again, PFC with a little bit of a fish coat at that time, detecting when two balls are talking to each other, or two discs, or two cracks. When are they within range of each other so that they're actually interacting? And you can see that at CI, you have mostly distributed cracks happening randomly through the sample. But at some point, the density of cracks becomes enough that statistically they're guaranteed to start interacting. And at that point, they start to take over. And you can see that middle curve ramping up very quickly once the cracks start to talk to each other. Great. So if we can get enough cracks, we can fail a sample through extension. But that's not always what we see in situ. We see a tunnel with a few very long persistent cracks going from top to bottom. How's that work? PFC did at this point, this was without the parallel bonds and everything. PFC wasn't great at this point in crack propagation. It was great at crack accumulation. So it was a kind of a test bed to study that phenomenon. We had to invoke fracture mechanics to take it the next step. And again, many people have looked at this idea that at extremely low confinements, cracks will propagate. Not uncontrollably, but almost. And that tendency goes away as soon as you get very small amounts of confinement. And that's globally in a continuum. This is again, PFC lets you look at the stress fields locally. You can see that even certainly at UCS, certainly at an unconfined state, and also in a confined state, there are fairly large islands of tension in your model, or at least stresses less than zero. And anywhere in those zones of low confinement, you could have crack propagation as well as accumulation. Now you're starting to cook with gas, right? And if you look at that you do a whole pile of runs, and you look at the top percentage, this is spatial extent of local tension. And so at around, this is almost increasing logarithmically, and you can see that around 20 or so, sigma 1 over sigma 3 of 20, 25, we're up to 10, and then if you continue this, it basically envelops the sample. Meaning, if you're here in this zone, you not only do you have accumulation of cracking, but you also have extension of the cracks, propagation of larger cracks happening, which then can have a much higher probability of interacting and or just extending. And that then all summed up led to this figure here, which is where we divided the world into tension, spalling, and everything else. And this is the so-called S-shaped curve, which is now, again, used fairly ubiquitously in rock mechanics. Not necessarily as an S-shaped curve, because that's really hard. But we needed to go from here then to find a way of putting this into a model. And the first attempt for me was to fake it in RS2 finite elements. I had to get Brent Corkum to change the dialog box to let me put a higher friction angle for residual than peak, because they locked you out. This idea that you have a high cohesive, low friction peak, that's the fraction mechanics. And then when that yields, the cohesion is lost, but the confinement dependency increases dramatically. And this was a neat way of both getting the ductile brittle behavior, as you can see, simply through the transition. Now, the only flaw here is that the hardening rule is not great. So this all sort of happens very quickly in the model, and there's some numerical issues that happen occasionally. Around about the same time, some people, including Ezra Dolmashid, who was my office mate, we were working sort of on these things in parallel, was working with the CWSF model. It wasn't called that at that time, but it was the ability to put friction, cohesion, tension, and even dilation, if you want to, into a table so that it evolved with plastic strain. Fabulous. And so these two models are essentially just different ways of doing the same thing. And in fact, one of the coolest figures, again, that was an inspiration, was this one. Pavel Vasic and Peter Kaiser, this was in the Rockburst handbook in the back somewhere, where they'd use this cohesion weakening model to look at how the brittle fracturing really increases as you pass a sine wave through, seismic wave through this tunnel. And I just thought the application of this was pretty neat. And so the work continued. But this dual model now allows us to look at the brittle fracturing on one side here. You can see this pillar on one side, near the outside of the pillar. This pillar has been driven through twice, but the older pillar is into the page. You can see the brittle fracturing on the outside of the pillar. And as you move just a little ways in, it becomes very solid. And eventually, and it's very difficult to get that, as long as that material remains, it's difficult to damage that internal core of the pillar. So you have brittle, and then you have, in this case, almost ductile behavior. And would it shock you if I told you this was salt? So salt at low confinements, think of salt as a creeping material, but at very low confinements, it behaves just like everything else. And of course, these models were great at modeling things we knew a lot about. We could simulate the URL with either the DISL model in RS2 or the CWS model in FLAC. We could even do a pretty good job when things got really hairy. This is the Niagara Tunnel. Again, it's a bedded material, but the beds are not really discrete. But it does, once the fracturing starts, the beds interact and really drive the spalling. And both models were very successful in predicting the actual extent of that model. And I've used this, and many people have used this now with RS2 in this case, to do real simulations and real analysis of what's happening in tunnels and predict behavior and even design. The caveat here is that now when you get into support design, you can model this brittle behavior. And if you use GSI, this looks very different, just for your interest. So GSI is based on shearing. This is based on spalling, and I won't show the other, but you can see the support trying to intercept that spalling deformation and deal with the deformations that are coming from the inelastic process. Now, here's the rub. So without some sort of useful dilation law, this gets really hard to make sense of or actually be real. And it comes back to that question. We're simulating something that looks real, but it's not entirely real. So we have to think about dilation. What happens after yield? And this Gabe Walton's work was very much on the brittle side here, looking at how dilation evolves with strain. and it's not always what you think. It does increase very rapidly at first and then starts to decay. Some very useful work from Lauren Lorg and Brona, just trying to understand what do we do about a rock mass. So somewhere in between here is brittle rock dilation. Where is he? Fedalberto in the front there is working with me on that, trying to sort that out. Moving on, this was another more significant figure taken back in the 90s by Brad Simpson at one of the mines up in Sudbury. What you're seeing there is a single joint that normally, if you look, you just ignore. It's at a high angle to the excavation. What difference can it make? But you can see the spalling fractures, which would normally come around and terminate in the excavation, get sucked over in a very interesting way by this soft shear structure. And what eventually happens, because you're supporting that, is it just walks up that joint and becomes, this was a 10,000 ton failure, which we're standing under, probably regretting that decision. And of course, structurally induced bursting at El Teniente on the right. So you can use these simple continuum models with pseudo-continuum structure, joint elements, to look at that interaction and come up with some very interesting conclusions. And it was the only way to explain this idea of brittle spalling interacting with, in this case, volcanic bedding. It was the only way to explain the genesis of these rock bursts. These were at 300 meters. Rock bursts have no business being at 300 meters, except for that interaction. I'm going to go a little over. So going on, I'll just go quickly, but trying again, moving into distinct element modeling, which is what really we're doing now mostly. This was an early attempt, again, with version 1 and 2, and you can see the pillar fracturing, the spalling on the outside of the pillar, generating that hourglass, and doing that self-confinement. And this was great. You can see the pillar stresses in the core. When you start to get damaged, they start to bend over, roll over, and eventually the core just keeps on confining itself and fails at a much higher stress level than you would otherwise predict. And this would not be possible with anything other than PFC to model this. And then, of course, quickly, PFC grew a lot after this paper with the contact models, famous lithophysical analysis. That was one of my favorite words for a while. Showing more and more elements, we could get smaller and smaller cracks forming and do more and more realistic simulations. This is some work from Fedalberto in the front there, coming back to this pillar idea and looking at how the nature of the yield changes as we fail. I'll let him, you can ask him some questions. He gave a little presentation. I'll have to skip that slide in the interest of time. UDEC, same thing. We get these pretty models. We can look at stress flow. We can create block models. This again is UDEC. We can let those blocks fracture. This was some work out of this program called Elfin, where we had this bonded block model, but in the blocks could actually remesh and fracture themselves. And this was a very, very advanced program, hugely computationally intensive. So it doesn't get a lot of use in rock mechanics, but you see the idea. The folks over at Geomechanica just made their triangles a lot smaller and got similar results. Really interesting work. Looks great. And you can do the same thing with this type of model at the sample scale. At the rock mass scale, you can look at the interactions between brittle fracture and, you can't see them here, but over in the right where it starts to get more intense, you can see existing structure. Almost there. And of course, we've used the 3-deck. This is some early work in our camp, looking at brittle spalling with bonded block models within 3-deck and 3D to capture this, both the hourglassing of the pillar, but also the internal confinement generation that happens inside. This is one example of a pillar that did this, and I've never seen any others. This is at Elliott Lake Mine in some sandstones. Really nice paper here. That's at this conference, kind of on the same vein. If you want to check it out by, I'm not going to pronounce that first name, but my good friend Navid, looking at this same idea of generating spalling fractures and seeing what happens. And then I'm just going to, I think where we're at today probably is this, which is courtesy of Hassan Gazvinian from ITASCA. They're integrating these bonded block models into a larger model surrounded by a continuum, and then looking at the continuum takes care of the evolving boundary conditions, and the bonded block model looks at internal fracturing and allows for fracture generation, dilation, everything else. And you can see the rough outlines just by squiggles of the bonded block model and the supported drift intersection there. And then the outer is being just responding to that. And then finally, we can do some support design. So we get the propagation, we get the depth, and we get the bulking or the dilation. Now the question is it right? Well, then we have to monitor and try to figure out if this is it's a great answer, is it the right answer? And so I'll just leave anybody who's still doing research. There's so much we still need to know. I would say we're still not capturing the true fracture extension and interaction processes here, but maybe what we're doing is good enough for now. But there's lots more to do, and this will be on somewhere. So just to finish up, so Colorful World of Oz is super cool. Looks real, feels real. You wish it was real, but just don't forget to visit Kansas every now and then and get back to some basics and figure out if it means anything.